In the previous module, we have considered simple null against simple alternative. But now we shall consider composite null against composite alternative. We consider some simple situations where these problems can be tackled. Consider a family of distributions px theta where theta is the leveling parameter and it is a member of a subset of p-dimensional Euclidean space where p is greater than or equal to 2. Our testing problem is null hypothesis is that theta belongs to omega h against ha, that theta is equal to theta 1, which is a known quantity, and theta is 1 is not a member of omega h. Next, define M of alpha h is the class of all level alpha tests for testing h. That means it is a class of those functions phi for which expectation of theta phi x is less than or equal to alpha for all theta belonging to omega h. Let small w theta be a distribution of theta over omega h. Small w theta is known and it is non-negative for all theta belonging to omega h. Moreover, integral of omega theta d mu theta over omega h is equal to 1, where mu theta is the measure on omega h. Here px theta is the PDF or PMF of x when theta is given. So px theta multiplied by w theta is equal to joint PDF or PMF of x and theta over script x and multiplied by omega h. Marginal distribution of x is then given by gwx is equal to integral over omega h of px theta w theta d mu theta, where x belongs to script x, and this is a known quantity when w theta is known a priori. Next, we consider the problem of testing hw, that x follows the PDF or PMF gwx against ha, that theta is equal to theta 1. Actually, GW represents the marginal distribution of x whenever w theta is known a priori. Next, for testing HW against HA, we note that HW and HA are both simple. So, we can apply Neyman-Pearson lemma for getting most powerful test for HW against HA, and this is defined by the function phi wx is equal to 1 if px theta 1 is greater than k of gwx. This is equal to alpha if px theta 1 is equal to k of gwx, and 0 if px theta 1 is less than k of gwx, with expected value under hw of phi wx is equal to alpha. Suppose such test satisfies expectation under theta phi wx less than is equal to alpha for all theta belonging to omega h, then such phi w is most powerful size alpha for h against ha. Now m alpha hw is equal to class of all level alpha test for testing hw, and that is the class of those phi for which e of hw of the function phi x is less than is equal to alpha. It can be easily shown that the set m alpha h is a subset of the set m alpha hw, and that can be proved by assuming that whenever phi belongs to m alpha h, we get that phi belongs to m alpha hw. Now, phi belonging to m alpha h implies that expected value of phi x theta of is less than is equal to alpha, which is equivalent to integral over x of phi x px theta d mu x is less than is equal to alpha for all theta belonging to omega h, and that implies integral of omega h and that of script x of phi x px theta w theta d mu theta less than is equal to alpha. Now, by Fubini's theorem, these two repeated integrals can be interchanged, and we get integral of script x phi x, and within bracket integral of omega h px theta w theta d mu theta and d mu x less than is equal to alpha, and which is equivalent to phi x gw x d mu x over the integral script x less than is equal to alpha, and that is equivalent to expected value of hw of phi x less than is equal to alpha. That gives that phi belonging to m alpha h implies that phi belongs to m alpha hw. So our conclusion is: number 1, phi w is most powerful size alpha test for testing hw against ha. Number 2, E theta phi wx less than is equal to alpha for all theta belonging to omega h. Number 3, m alpha h is a subset of m alpha hw. To conclude that phi w is MP within m alpha hw by the statement 1, that implies E theta phi wx greater than is equal to E theta phi x for all phi such that phi belongs to m alpha hw. That implies E theta phi wx greater than is equal to E theta 1 phi x for all phi belonging to m alpha h by statement 3. Again, by statement 2, phi w belongs to m alpha h. So we have phi w is most powerful for h against ha within m alpha h, and that gives the result. Next, we consider some examples in which we assume that x is equal to an n component vector having the elements x1, x2, xn with xi following n mu sigma square I is equal to 1 independently, where theta is equal to mu sigma and parametric space is R multiplied by R plus, that is a subset of R square. That means here P is equal to 2. Testing problem we consider is H1 is the set of those elements in the parametric space for which sigma square is greater than is equal to sigma naught square and mu remains unspecified, against HA1, the alternative one, is that sigma square is equal to sigma 1 square, which is less than sigma naught, and mu is equal to mu 1. And the next testing problem is H2, that sigma square less than is equal to sigma naught square and mu remains unspecified, against HA1, that sigma square is equal to sigma 1 greater than sigma naught square and mu is equal to mu 1. Next we get the solution of this problem. Sufficient statistics for mu and sigma square is T is equal to vector of summation xi and summation xi minus x bar square, which we denote by u and v. So test based on x is equal to x1, x2, xn has the same power as that based on uv. For each test phi depending on x1, x2 and xn, we can find another test psi depending on uv such that phi and psi have identical power functions. So without loss of generality, we consider the test to be dependent on uv if required. Let w theta be a non-negative weight function on sigma square is equal to sigma naught square. That means w theta is equal to w mu sigma naught square over unrestricted space mu with the property that w mu sigma naught square greater than is equal to 0 for all mu, and integral over mu of from minus infinity to plus infinity w mu sigma naught square d mu is equal to 1. Here we have the following likelihood function: px theta is equal to c sigma to the power minus n e to the power minus 1 by 2 sigma square summation xi minus mu whole square, that is equal to c sigma to the power minus n e to the power minus v by twice sigma square into e to the power n by twice sigma square into u minus mu whole square. We know u and v are independently distributed, where u is normal mu sigma square by n and v by sigma square is chi square with n minus 1 degrees of freedom. So p uv theta is equal to c1, where c1 is a constant, multiplied by sigma to the power minus n, v to the power n minus 3 by 2, e to the power minus v by 2 sigma square into e to the power n by 2 sigma square u minus mu whole square. Since the hypothesis HW is x, follows the PDF GWX, where GWX is equal to minus infinity to plus infinity of px theta w mu sigma naught square d mu, we get p u v h w is equal to c1 sigma naught to the power minus n, v to the power n minus 3 by 2, e to the power minus v by 2 sigma naught square multiplied by integral minus infinity to plus infinity e to the power minus n by 2 sigma naught square u minus mu whole square w mu sigma naught square d mu, and that is a known quantity. Therefore, px theta 1 is equal to p u v theta 1 is equal to c1 sigma 1 to the power minus n, v to the power n minus 3 by 2, e to the power minus v by twice sigma square into e to the power minus n by 2 sigma square into u minus mu 1 whole square. Hence, we get the likelihood ratio R is equal to C1 sigma 1 to the power minus n, v to the power n minus 3 by 2, e to the power minus v by twice sigma square into e to the power minus n by twice sigma 1 square into u minus mu 1 whole square, whole divided by C1 sigma to the power minus n, v to the power n minus 3 by 2, e to the power v by twice sigma naught square integral minus infinity to plus infinity e to the power minus n by 2 twice sigma naught square u minus mu whole square w mu sigma naught square d mu. Consider the following weight function. W mu sigma square is equal to 1 if mu sigma square is equal to mu 1 sigma naught square and 0 otherwise, and that gives R as C1 sigma 1 to the power minus n, v to the power n minus 3 by 2, e to the power minus v by twice sigma 1 square, e to the power minus n by twice sigma 1 square u minus mu 1 whole square, whole divided by C1 sigma naught to the power minus n, v to the power n minus 3 by 2, e to the power minus v by twice sigma naught square, e to the power minus n by 2 sigma naught square into u minus mu 1 whole square, and that gives C star is equal to e to the power minus 1 by 2 sigma 1 square plus 1 by 2 sigma naught square whole thing multiplied by summation xi minus mu whole square, which decreases or increases with summation xi minus mu 1 whole square according as sigma 1 square is less than sigma naught square or greater than sigma naught square. Hence, using the weight function, a most powerful test for HW against HA has the critical region W1 is equal to set of those x for which summation xi minus mu 1 whole square greater than k1, and W2 is equal to set of those x for which summation xi minus mu 1 is less than k2 according as sigma square is greater than or less than sigma naught square, where k1 or k2 is such that probability under HW of W1 is equal to probability under HW of W2 is equal to alpha. So under HW, summation xi minus mu 1 divided by sigma naught square follows chi square with n degrees of freedom, and k1 and k2 can be calculated from the percentile points of chi square n distribution. Now we have to verify that under the above weight function, probability measure under theta of wk is less than is equal to alpha for all theta belonging to omega h for k is equal to 1 and 2. Here, probability measure under theta of w1 under mu sigma square is equal to probability measure under theta of summation n of xi minus mu 1 whole square divided by sigma square greater than is equal to k1 by sigma square under mu and sigma square, and that gives probability under theta of y greater than is equal to k1 by sigma square under mu sigma square, where y is non-central chi-square with n degrees of freedom and with non-centrality parameter delta square, that is equal to n into mu1 minus mu whole square divided by sigma square. It can be seen that y greater than c is increasing in delta square for fixed c and n, which implies probability that y greater than c under delta square greater than 0 is greater than is equal to probability that y is greater than c under delta square is equal to 0. Here we require that probability under theta of W1 under theta is less than is equal to alpha for all theta belonging to omega h, but this is not satisfied for W1. Hence, we conclude that the test W1 is not most powerful size alpha for h that minus infinity less than mu less than infinity and sigma square less than is equal to sigma naught square, versus h that mu is equal to mu1 and sigma square is equal to sigma 1 square, which is greater than sigma naught square. Let us now consider probability of W2 under mu sigma square, which is equal to probability that y is less than k2 by sigma square under mu sigma square, which is less than probability that y is less than k2 by sigma square delta square is equal to 0, and that is equal to probability that y is less than k2 by sigma square under delta square is equal to 0 for all sigma square greater than sigma square, which is equal to alpha. Thus, W2 is most powerful test for testing that h of mu belonging to minus infinity to plus infinity and sigma square greater than sigma naught square against h that mu is equal to mu1 and sigma square is equal to sigma 1 square less than sigma naught square. Alternatively, set W star theta is equal to W star mu sigma square is equal to 1 by delta root 2 pi e to the power minus 1 by twice delta square mu minus mu 1 whole square. Mu is greater than minus infinity less than plus infinity at sigma square is equal to sigma naught square and 0 otherwise. That means x bar given mu and sigma naught square follows normal distribution with mean mu variance sigma naught square by n, and mu marginally follows normal distribution with mean mu1 and variance delta square. Combining these two, we get x bar follows normal distribution with mean mu1 variance delta square plus sigma naught square by n. To choose delta square such that delta square plus sigma naught square by n is equal to sigma 1 square by n, which implies delta square is equal to 1 by n sigma 1 square minus sigma naught square. Thus, we get that x bar given W star is normal with mean mu and variance sigma 1 square by n. Here we find most powerful size alpha test for h omega that x follows p W star theta is equal to c1 into e to the power minus v by twice sigma naught square into e to the power minus n by 2 sigma 1 square into u minus mu1 whole square multiplied by v to the power n minus 3 by 2 versus HA, the alternative, as mu is equal to mu1 sigma square is equal to sigma 1 square greater than sigma naught square. The likelihood ratio for the above test is given by Px under HA divided by Px under HW star, which after simplification reduces to some constant multiplied by e to the power minus of 1 by twice sigma 1 square minus 1 by twice sigma naught square into V, which is increasing in V. Hence, most powerful test for HW star against HA has the critical region W3, which is the set of those x for which summation xi minus x bar whole square greater than K3, where K3 is such that probability under HW star of W3 is equal to alpha, which implies K3 is equal to sigma naught square multiplied by chi square n minus 1 alpha. Also, it can be shown that probability under W3 under theta less than is equal to alpha for all theta is equal to mu sigma square such that minus infinity less than mu less than infinity and sigma square is less than is equal to sigma naught square. Now, probability that summation xi minus x bar whole square divided by sigma square greater than k3 by sigma square under mu sigma square is equal to probability that chi square n minus 1 greater than chi square n minus 1 alpha into sigma naught square by sigma square for all mu such that minus infinity less than mu less than infinity. That means which is less than probability chi square n minus 1 is greater than chi square n minus 1 alpha for all mu greater than is equal to minus infinity less than infinity, and sigma square is less than sigma naught square, and that is equal to alpha. Thus, the above test is most powerful size alpha for the null hypothesis that mu is greater than minus infinity less than infinity with sigma square is less than is equal to sigma naught square against HA that mu is equal to mu 1 and sigma square is equal to sigma 1 square greater than sigma naught square. Since W3 is independent of HA, the test is also UMP size alpha for the testing problem H that minus infinity less than mu less than infinity and sigma square is less than is equal to sigma naught square versus HA that minus infinity less than mu less than infinity and sigma square is greater than sigma naught square. In this module, we have discussed two typical testing problems in which uniformly most powerful test exists for one problem and for the other one uniformly most powerful test fails to exist. In the subsequent modules, we will consider more than one parameter family of cases for which we can obtain more general results for this testing problem.